this database storage layer, and we covered these major aspects. We started looking into storage technologies, and in here we realized quickly that there is a major speed gap between the various storage levels we have. And this is a major challenge for database. It's to try to address that speed gap between memory and disk. Okay, and it makes use of a lot of smart techniques to achieve this, addressing this gap. So one of such techniques is to use parallel read and write. And to achieve this parallel read and write, there is a technology called the RAID, redundant array of independent disks. And this technology, as I explained, is heavily used in the database world. Almost every database in practice will use some kind of RAID to basically manage the files of the database. Then we dived into how the actual data is stored in files. At the end of the day, the data that we store in databases is stored in a file, and we discussed how the actual files are organized. So the only thing we didn't really discuss is the buffer manager, and this is one of the techniques used by the database to address this speed gap problem. So the idea of a buffer manager, anyone can give some what come to mind when you hear this buffer manager?
It keeps the most recent transactions before they are updated on the database.
Yes, basically, yeah, kind of the database will reserve some memory location as some, we call them frames. And these memory locations, we will be loading, if you remember the file, the database file is made up of blocks. So when we read, the unit of reading and writing in a database is a block. We will never read or write one particular record. We read the whole block and then we write back the whole block. Now, when we read these blocks, we read them, of course, in memory. So when we are done with them, when a particular transaction reads certain blocks and it's finished using them to answer certain query, let's say, it does not throw them away or throw them out immediately. It keeps them in memory with the hope that subsequent transaction or subsequent queries will make use of them. So this way, we don't want to go all the way back to the disk. So that's why database systems, the more memory that you throw at them, the happier they are. And they also, database system happens to be very selfish. They don't want other systems to coexist with them because they really work best as more memory we throw at them, the better they become. Because they are able to cache those data blocks and not get rid of them and keep them for subsequent usage. And this will boost performance significantly. That is one of the major components. So let me just jump directly to this part, because I really want to get to the indexing, inshallah, today. So this is the idea of a buffer manager. So database has a buffer pool which is maintained in memory, and this buffer pool acts as a cache. This concept is not really new. It's used by other systems, operating systems, and are also using this concept. But database heavily relies on it. So and the buffer pool is nothing but a memory region, which is an array. You can think of it as an array, contiguous array of memory region that is divided into what is known as a frame. So you can think of it as a big chunk of memory reserved by the database, and it's divided into pieces. And those elements in the buffer pool are called frame. It's just a terminology. So on the disk, On the disk, the file is divided into blocks, or another term for it is page. Whenever you hear a data block or a data page, synonym. Either term is fine. Now, in the buffer pool, they use the concept of they name these locations as frames. Okay, and guess what? The size of the frame is exactly the same size as the page. Remember, databases they divide the data file into pages or blocks of fixed size, and usually between 4 kilobytes to 16 kilobytes. So for example, in SQL Server, I think they use 8 kilobytes. So the buffer pool is also divided into chunks of fixed size. And the size of those chunks that we call frame is the size of the page. Okay, so when some DBMS component, typically the query engine, requests certain page to go from disk to the memory, it gets loaded to one of these frames. That's basically the idea. So the higher, remember, in the architecture of the database, we have the disk manager, we have the buffer pool, we have what we call access methods, and on top of that, we have the query execution engine and so on. So the upper layers, they assume whenever they need some pages from disk, they assume it will be available in the buffer pool. So the buffer pool, you can think of it as hiding the existence of a disk. So the upper levels, they don't deal with disk directly. So the buffer pool isolates the remaining components of the database from dealing with disk. They only see, so it enables higher level DBMS component to assume that the needed data is already in memory. So this is the role of the buffer pool. It encapsulates or hides the details of the file system. And the upper components, they only deal with the buffer pool. They don't deal with the disk directly. Okay, so that is the idea. So in here, when we deal with this, when we design this pool manager, one question that's come to mind, we might say, okay, the operating system also has this ability of caching, let's say, file parts or files. But as I mentioned, we cannot rely on the operating system functionality to manage the database. In fact, database implements Yes, recording, but I forgot to put this. It's fine, it's still recording. Okay, so the database relies on its own file reading and writing, its own file manager, its own buffer pool. It does not rely on the database. It does not rely on the operating system to provide these services. So if you write something like let's say, Java application or an application yourself, and whenever you're dealing with files or dealing with disk, you rely on the OS. You are just using API provided by the OS to read and write these files. But in case of database, it does not rely on OS. It does it itself. So it reserves this big chunk of disk. Let's say it reserves a file from the operating system. The inner working inside the file, how data is organized, how we read and write blocks, it's not under the control of the OS, it's under the control of the database. Same thing for the caching and the buffer pool. It's not under the control of OS, it is under the control of the database itself. And the reason why the database has a lot of information that can help to do better management of the pool. Later on, we will see later on, during the query execution, it can anticipate in advance what blocks it needs, and it can go ahead and fetch them. The database, The OS does not have such information, so it cannot help do this optimization. So that's why although some of the functionality you see, you might think, oh, it's replicating what the OS is doing. Not really. Kind of replicating, but it's doing it in a much better way because it has more information than the operating system. So that so databases, they don't rely on OS to manage files. They don't rely on the OS to manage the buffer pool. Okay, all right. So for the buffer pool to really work, so database need to maintain this page table. Okay, so this page table, what this page table maintains, it's kind of an array that maps page number or page ID to a frame ID. So whenever somebody or whenever a component in the upper component in the database, such as the query engine, asks for a particular page, let's say page number 5, first thing the database, the buffer pool will look up in this pool. It will look up in this page table. It will find whether this page that is requested is already in the pool or it's not in the pool. So if it's already in the pool, then whoever is requesting this page, they will hand over a reference to the frame in which this page is already loaded. If the page requested is not on this page table, then the buffer manager will go to disk, will fetch it, put it in one of the empty frames, and then store a reference, store a mapping where this page that's just been loaded, in which frame it is stored. Okay, so this is kind of a lookup table, very simple lookup table, mapping for each page that is loaded in which frame it is loaded, so we can get to it. So the buffer pool maintains this page table. Not only this, it maintains these two important flags, a pin count and a dirty flag. Two flags associated with every page that is loaded in the pool. So the pin count, as the name indicates, it just tells us how many current transactions that are running are making use of this particular page. So we might have, let's say, 5 or 3 transactions running, and they are generating results for some query. And while doing so, they are using some pages that are already on the buffer pool. So this pin count helps us not to throw away the pages that are currently in use. So we can only kind of replace or throw out pages where the pin count is 0. No concurrent transaction is currently used. So you can already tell whenever a transaction wants to make use of a page from the pool, it increments this pin count. When it's finished, it decrements it, so we know whether this page is currently in use or not in use. What about the dirty flag? What this dirty flag is for? So this is an indicator. It's a flag that indicates whether the page has changed or not changed. Yeah. So for example, if the dirty flag, if there is a transaction that changes something in the page, it will set this flag to true. And this is very important because it indicates to the buffer pool, be careful with this page. Before you throw it away, make sure you push it to disk. Yeah, so this is very important flag. So this page table, you can think of it as some kind of dictionary. It contains the frame. For each frame, what page is currently loaded in this particular frame, and for each frame, how many concurrent transactions are currently using this frame, and whether this page has changed or not. So that's what the buffer pool maintains for it to work properly. Okay, so you might be surprised in why don't we just save the changes immediately to disk once the transaction commits. That doesn't happen. why we don't immediately save to disk in a hurry. Once the transaction commits, we go ahead and persist or push the page to disk. Why do? No, remember the page or the frame is already a block.
There might be changes on the page. So
All this is to address the speed gap. Remember that the input-output is very costly. So we try to delay it as much as possible. So we can make changes in memory, and these changes are not persistent to disk. When do you think these changes will be persistent to disk?
when it's removed from the pool.
When we try to remove it from the pool. Yeah? Even if transaction commits, by the way, even if the transaction commits, the dirty pages are not pushed immediately to disk. Okay, but you might, if you remember, we have this acid properties. One of the acid properties is durability, and this is contradicting durability, yes, because the changes we are making are all in memory. But how does the database achieve? At the same time, why are we doing this? Why are we keeping changes only in memory? Why are we not pushing them to disk? What is the reason? Performance, for better performance, because it's an expensive operation. But at the same time, we promise the outside world that we will give them durability guarantee. So how does the database achieve these conflicting goals? Sorry? Through logs. So what I mean here, when a transaction commits, what it will do, it will save only the changes that were made. For example, if I read a block that has, let's say, hundred student records in one block, and I change the phone number of one particular student, which is basically I'm changing only one column, only one column changed. So the log will just say the phone number this is the old value, this is the new value for student 1, 2, 3. So one small tiny change. And of course, database has so many concurrent changes going on. So we put these concurrent changes in a log entry, and when we commit, what we save to disk? The log, but not the actual dirty page that has changed. Of course, we do the change in the actual page in memory because it's very fast. We deal with memory super fast, but we delay pushing that change to disk until we are ready to throw away the page. In some databases, they have some background process that can do this periodically, wake up and say, database is not doing much. Let me take those pages that are dirty and push them to disk. So later, when we throw them away, we don't need to waste time pushing them to disk. So there are two ways to really push dirty pages to disk. Either wait until we need that space and we need to throw away the page. Before we throw it, we say, oh, is it dirty? Yes. First, push it to disk and then throw it away. Okay? Or there might be some background process doing this in the background when the database is not busy. So two approaches.
Sorry,
Yes, please.
Yes, there's a power outage.
Yeah.
The buffer data is lost.
Yes.
So then we recover from log.
Yes, very good. So basically, what the database does, when you restart your database, usually it takes a little bit of time. I have seen this in practice. In a real production database, when something crashes, it takes a bit of time to recover. For example, let's say people started working from 8 to 12 and the crash happens at 12. Maybe most of the changes especially if it is a database with lots of memory, maybe most of the changes are only in memory. So, but of course, the changes, all of them are persisted to disk in a log. So the first thing database does when it restarts, it will go through the log and replay the log from the last time. So the log has some indicator where is the last time the log was applied, and then it will replay the log, which means all the changes people have been doing from 8 a.m. to, let's say, 12 p.m., will be redone on the actual database, on the actual files, so, on the disk. Yes.
Also, Lru manager.
Pool is mainly used for a live database, a database that is used live and online, and people are using it. We are caching those blocks that we read from disk with the hope that some subsequent queries will make use of them, and we don't need to go back to disk. Availability, as we discussed now, is achieved through what? Through logs, logging all the changes. And once we commit, before we say transaction is committed, we need to make sure the log entries are persisted to disk. Not necessarily the page itself. We don't need to push the page, we push the log to disk. That will ensure durability. Now for isolation, there are mechanisms we will see later on, usually based on locking. So in a page, let's say you want to update certain record in a page, then you will lock it. You put a lock in there, so no other transaction. There are two types of lock, shared lock or exclusive lock. If you want to change, to update something, you take an exclusive lock, which means nobody else can read or write that particular record until you are done. Yeah. Once you are done, you release the lock, so others can read and write it. So that's different mechanism.
Can read or write, or they can read, but they didn't.
Depends. Like if you are, let's say, if you are updating, then if you are updating,
You can read, but you can't change it. This is in the.
no, if you are reading, if you are updating, you should not allow. If you are just updating, you should not allow reading. Otherwise, you will end up with dirty reads, because your transaction might roll back.
It's depending on the environment.
No, not environment. Basically, we will see. We'll see this. The isolation, we will see later on. There in the database, there are different levels of isolation, depending on the application. Do you want others to? Do you want to allow dirty reads? You don't want to allow dirty reads? But in usually the default behavior in most databases, when you are about to update, it is locked exclusively. Nobody can read it or write it until you are done. Of course, that takes fractions of seconds. That's why you never, those of you familiar with real development, you never do, let's say, begin transaction and you start interacting with users. Because once you do begin transaction, it might lock some record nobody can read or write until you commit. So between begin transaction and commit, you don't have any user interaction. You collect all the data from users and you're just about to update or insert, or especially for update. You're about to update, you do begin transaction, do your update, and you do commit. Between begin and commit, that record, only that particular record you try to update will be exclusively locked for those nanoseconds. Because remember, all this is happening in memory. It's very, very super fast. And as good practice, developers need to be aware that when they do begin transaction and commit transaction, in between, never do any interaction with users. Because users, somebody might call them or they might go and get coffee, whatever it might happen, and everything is locked. Yeah? So you do it the last minute. You acquire the transaction at the last minute, you do the work super quick, and you let others come in and make
So for
use of
that,
it.
there is time sometimes for inserting.
No time. Like basically, the others need to wait. The others that trying to update or read, they need to wait until you release the lock. Yeah, we will see this, of course, in much more details. The locking is just one mechanism. There are other mechanisms such as multi-version and so on. It's a big topic.
In real life, sometimes if you want to update or insert something, you have time for this.
What do you mean time?
For example, time to insert data, or this page will be locked. Sometimes it will
but that is like usually enforced at the application level, not at the database level. Maybe you mean, for example, let's say when you create a session, when you log in, you have certain time after that you your session expires and you have to log in back again. But that is application level, not at the database level. Okay, database level, it does it at the operation. When you actually say, let's say, update student phone number equal 556555, where student ID is 123. At that time, that record student record 123 will be logged. Just for that nanosecond time it takes for the update to take place, and then the log will be released. Yes. Okay. Yes, please.
So the logging
Yeah.
for each of the changes that happen with the database.
Yeah.
How much would you log? So you log until you commit and you write to the disk, or you log until like you continuously log?
No. You basically every transaction. So you remember, like transaction usually, if you are putting multiple statements you can basically encapsulate them in one transaction. If you are not encapsulating multiple statements in a transaction, so every statement starts and commits its own transaction. Okay. So what I mean is, when I say begin, and then I put a couple of statements, begin transaction, puts a couple of statements, and then commit transaction. Yes. So all the changes that I make in these statements between begin and commit, they are logged, they are recorded. What are the changes that are made? So before I say commit and confirm to the user that your changes has been finalized and made permanent, I take these changes and push them to disk. Otherwise, I cannot say to the user, I have committed your transaction. Because remember, transaction provide this asset, the D. The D in the asset means durability. If something crash, I will not have the ability to honor this commitment that I gave. Yeah, because remember, there are two things here. The data pages or the data blocks in memory, they have changed also, but those changes volatile, because I have not pushed them to disk yet for performance reasons. And so I am basically here committing, doing this trade-off, boosting the performance by delaying pushing the dirty pages as long as I can. But at the same time, I need to honor the durability guarantee that I gave. So to honor the durability guarantees, I will be doing, as I explained, logging the changes and pushing the changes, hoping that the log change is much smaller than the actual block. In a log, let's say a block recording logs, it might be able to record many logs from multiple concurrent transactions. So when I push, I'll be pushing the logged changes of multiple transactions. But even if there is no concurrent transaction, only me in the database, I must push that log to disk. Yeah, I must push it. Otherwise, I will not be able to honor the durability property.
Sometimes you have a function called the flash. What does it do? Doesn't it push me physically?
Flash, maybe we've seen this in the context of file management, or in the context of let's say, for example, JPA. There is something called flash, but those are changes that are made locally in the entity manager. Those of you using GPA, those changes that are made in the entity manager, I am basically pushing them to the database. But that does not control the buffer pool. The buffer pool is something internal component within the database. There's no API to directly access it or directly manipulate it. Yeah. So your transaction might be fully committed, but your dirty pages are not yet in disk. Yeah. Because in all cases, if somebody requests, let's say you changed page 3, and somebody requests it, we will not go to disk anyway to answer that, to give them that particular page, because we already have it in memory. So in memory we are fine, it will have all the changes. But the only problem if something happened and system crash, all the the changes in the dirty pages will be lost, of course. But we can reconstruct them using the logs. Yeah. Okay, so moving on. So this is what I just explained. So the pin count allows us to track the number of threads that are currently accessing a particular frame. And before we evict or before we throw out any of the pages, we need to make sure the pin count is 0. We cannot throw something some other transactions are still working on. And for dirty flag, if it's set to 1, before we throw the frame away, we push it to disk. Okay. Okay, so when a page is requested, okay, so when a particular page is requested, the pool will look into the buffer pool. If there is some empty frame, no problem, we will load the page into that particular frame and add an entry to the page table, to this table that is mapping the frame to the page. That's all we do. Now, if there is no space available, then there is a problem. We have to find some space. And this is where a huge set of algorithms and papers, and this is very, very old problem of cache management. How do we evict which pages or which frames we will empty to make space? So in here there are policies, different policies and different algorithms to help us do this. So what do you think? What could be some of the policies to evict pages?
All of the less used pages, pages that are not requested frequently as frequently.
Not requested frequently, or
the pages that have the pin count 0.
but many of them might have pin count 0. Many of them. Yeah. Maybe first in, first out, which means the oldest ones that we loaded some time ago, we throw them away first.
But first in, first out, and pin count.
First in, first out. Yes, that could be yes. But there are better policies. The best one of the best ones is LRU policy, which is least recently used. Least recently used. So for each frame, the buffer pool could maintain a timestamp where this particular frame has been used, and basically you can think of we can go to this page table, order them by timestamp last used timestamp, and take the ones that are not recently used and evict them, because the most recently used are more likely to be used again. Right? So this is one of the very popular algorithms for eviction. Okay, of course, before we evict, once we find our candidate page to evict, then we do the checks that I discussed. The pin count should be 0, and if it's dirty, we first push it, then evict it. Okay. Okay, so I already mentioned this. So in here we need to talk about this buffer replacement policies. Buffer replacement policies. Many policies are there. The most common one is the least recently used, LRU. LRUK, there are variations I will explain. LRUK, there is a private pool space per query and priority hints. These are the major policies that are used for buffer replacement. So let's just go through quickly some of them. So the least recently used policy, so the buffer pool will maintain timestamp when each page was last accessed, and when the DBMS need to evict a particular page, it will go and throw out the ones with the oldest timestamp. Okay. Now to optimize the implementation of this least recently used, because we want to make it as fast as we can, there is instead of having a timestamp, there is a much less costly way of doing it, which is known as a clock, which is an approximation of LRU with less overhead. So remember, we want to do this buffer management with the least overhead possible. So in here, basically, let's imagine our buffer pool, which contain pages loaded into frames. Imagine them in some kind of circular data structure or a circular layout. Imagine them in a circular layout, and we have some kind of hands moving clockwise. Yeah. So basically, this hand will be moving whenever we need to evict a particular page. We move this hand to tell us which page should we throw away. Okay. So what will happen is, so when let's say the page will start here. The page will start here, for example. A ref count, whenever the page is used, whenever the frame is used, the thread that uses this frame will set this ref to 1. Okay, so let's say I start my hand, initially I put my clock hand in here, and this ref was set to 1. So I leave it. What I will do, I will say I'll put you to 0, but be careful. I'll come back to you later. Then I move to the next one. I'll say if ref is 1, I set it to 0 and move to the next one, hoping that one of these refs is 0. So basically, I keep this hand moving clockwise. Whenever the page is accessed, the ref will be set to 1. When I visit it, if it's 1, I set it to 0. I basically move to the next one. If it's 1, I set it to 0, and keep moving until I find an entry where the ref is 0, and that's the one I throw out. Yeah. So it is an approximation of LRU, but much more efficient, because in here I'm not maintaining any timestamp and not wasting any memory. Much memory. In here, it's very small bit, 1 bit, to store 0 or 1, versus having a timestamp, and I have to sort the list to take the entry with the least timestamp. So this approximation is very nicely, very practical. That's what many databases use instead of maintaining timestamps. It's very simple one. Of course, the buffer manager keeps track of where this hand is actually waiting at. So we keep moving it clockwise. So for example, if I evicted this, that one is evicted. So basically the clock, this hand of the clock, it will be pointing to page 3. Yeah. And next time we need to evict, we will see if the ref is 1. If 0, we throw that page immediately without even thinking. If it's 1, we make it 0 and we move to the next one. And that basically keeps on moving that way. Now the LRU clock is just a simplified implementation and efficient implementation or approximation of LRU. But LRU has a major problem known as sequential flooding. Sequential flooding. What happens is, if some transaction or some thread runs some transaction that reads so many pages, let's say somebody is trying to get the average GPA in QU. So to get the average, it will need to read all the students and all the student, let's say, records, bring them all into the buffer. And of course, this will throw away all the pages. Yeah, will throw away all the content of the buffer. Yeah, and maybe this getting the average GPU is not really the pages that we load. All these pages that we load, most likely we will not. Other transactions will not make use of them in the near future. So basically, we've thrown away some valuable pages that we might need in a very near future, and we replace them with some pages that are very specific to that particular query, and that particular query might be not very frequent. So we end up with what is known as the polluting the buffer pool with frames, or sorry, with pages that most likely are very specific to that particular query, and not with very unlikely or small chance of reuse in the near future. So this is a problematic. And the most recently used, which is in this case the most recently used, will be the pages loaded to answer this query that required loading so many pages. So this is a problem. So here is the illustration of it. So for example, here is my query. Yeah? The first query. In here, I'm querying this table A and getting all the record, all the fields where ID is 1. Yeah? Okay. This is my buffer pool. So basically what I'm trying to do here, yep. So for maybe to answer this question, I have maybe loaded this page from the disk, loaded into the buffer. Yeah. Then the query 2 came in, and then it wants to do average val of A, of this table A. So basically it needs to go through and bring all these pages from table A, from the disk. So when it brings these pages, of course, page 0, 1, 2, no problem. We have them already in memory. Once we reach page 3 and 4 and 5, we have to throw away this. Yeah. So once we throw them away, so basically if this query comes back again, because maybe this one is very frequently used, we will look up in the pool and we will not find any. We will not find those cached pages that we can just readily use. We have to go back to disk. All of this because of this this query that is has flooded our pool and polluted our pool and thrown away much more useful pages than these pages that require to answer query 2. So this is what it means by sequential flooding. So in here, from the previous, to answer the query 2, I had to load page 3, 4, and 5. And then suddenly, this query, which is frequent, it came back again. Somebody is trying to execute it. And then, unfortunately, the page is not there because all the available space in the buffer has been taken by this big query. And then we had to bring this page again. Yeah. So the least recently used LRU policy suffers from this sequential flooding. Yeah. That's one of the major drawbacks. So how to solve this? So one way is to do what is known as LRQ. So track the history of K references as timestamp and compute the interval between the subsequent accesses. So not only we keep track of the timestamp of the last access, we keep track of the duration since this particular block was last accessed. So this way we can estimate the next time that page is going to be accessed. So for example, in here, if this one is very frequently accessed, so we will not give it away we will not give it away because the periods between subsequent access, I mean the duration between subsequent access, is very, very short. So this is a good candidate of a page that needs to stay there. So just using the timestamp is not enough. You need to also keep track of the duration between subsequent calls. Yeah? If this duration is big, like this, maybe this page we need it, but maybe every hour we get a request for it. That page we can throw away. But the ones let's say every minute or every second we need that page, we better keep that. So you can think of it as an enhancement of LRU that take into account not only the timestamp of last use, but also the interval between subsequent usage. The smaller these intervals, the more likely we should keep the page in memory. The other one is to have a private pool space. So instead of, for example, for this particular query here, instead of letting it flood the whole buffer, we can basically limit the number of pages this particular query can take. So we can say, okay, this query, yes, we were ready to answer it, but we will only allocate to it 5 pages. So this way it will not flood the whole buffer. So we can allocate private pool per query. So instead of giving a particular query, the whole pool, and this will result in evicting so many pages that are popular that we need them, we just say, okay, we will give you 20% of the pool, no problem. Make use of it as you wish. And this way we are protecting the pages that are frequently used. We don't just throw them away just to serve one query and then make other queries suffer because of that. So we give it just a small part of the pool rather than the whole pool. Yeah?
The 20% is not enough.
Then basically this query will take a little bit longer. So for example, in here, the average. So in the average, what you're doing, you are maybe accumulating this value, accumulating it, and you are accumulating the count. So you keep loading more pages, which means it will take a little bit longer. But that's fine. Only one query performance will be degraded, but not all others. So you are limiting, especially for these queries that are humongous and they need to load so many pages. Because this particular query, especially this aggregate query, there is no escape but to load the whole table. All the pages need to be loaded in memory for us to answer this query. So we know that this will be polluting and flooding our pool. So we don't let it to do that by limiting and putting a cap on the number of pages or number of frames this particular query can use. And this way, we are affecting the performance of that query and not letting it affect the rest of the system. It's clear? Yeah. The last one, which is a very practical, that the DBMS provides some priority hints. This will become clear as we move through the indexing. There are some pages very critical. You will almost never throw away. So when the buffer pool loads them into, or when they are loaded in the buffer pool, they are marked as high priority that shouldn't be thrown away, no matter what. Yeah. So example of such priority, high priority frames is the root of B tree index. Of course, this might not make sense now, but you will understand this as we move forward. The root of the index is so critical. Whenever we query this table, the first page we look at to guide us on how to retrieve the relevant pages to answer the query, the starting block we look at is the root of the index. So what I want to say here, let's say I am looking for, let's consider this as the ID, as an example. Let's say this is a student's ID. I'm looking for students where the ID is greater than 300. Okay, so from this index, it will tell me, this root index, it will tell me go right. Look at the right side of the tree. You can safely ignore this whole part. Okay. Of course, we will go through this in much more details, how the index work and how do we build this tree. But basically, this root page of the index is so critical. Through this root page, it will guide the search process, whether in the tree, whether I will go right or go left to actually answer my query. So suppose this is a student table. Anyone who wants to query the student table, they must look into this root index. Root page of the index. This root page, once loaded into memory, we should keep it there. We should not throw it away. How we will do this? By putting some priority hint on that particular frame, saying to the buffer pool, this is kind of untouchable. So critical, keep it there. Go and find somewhere else, some other frames or to throw away, not this one. Because it has a major impact on many, many queries. So we keep it in memory. So the root pages of indexes, as an example, are always kept in the buffer pool to boost performance. In fact, in here, if I want to answer my query, all I do, I need to read 2 blocks. I need to read this block and this block, 2 blocks only. I already saved the read in 1 block. So every query will have 1 block less to read. So the cost of this query will be 2 blocks instead of 3, as an example. Yeah? Okay. So that's it for the buffer pool. Prefetching, yes, another one is prefetching. The buffer pool, and this is where we want to manage our buffer pool ourselves. The DBMS don't rely on the OS to basically don't rely on the OS to manage the buffer pool. It manages the buffer pool itself. Because, for example, here from this query, you can see here this query is asking for, give me all the records where this particular attribute is from 100 to 250. Okay? From the index of that particular table, we will discuss what the index is. From the index already tells us you will basically, in this tree, you will go left, load this, and then the system already knows you need to load these 2 blocks. So the database will, in advance, load these blocks. While the CPU, let's say, is processing this block, this one and this one, we already loaded this. And all of this is to try to address, as I told you, the speed gap. The CPU and memory is so fast, and reading and writing to disk is so slow, relatively. So we want to be as ahead as we can. So prefetching really helps. And also, for example, for this one, to answer this query, database, the second query, database knows that there is no way to answer this query. The only way to answer it is to go through all the pages of the table. So it will just close its eyes and start fetching all the pages a priori. Okay? Even before the query engine or the query component asks for it, because it knows it will need it. So it tries to be ahead as much as possible to kind of try to reduce that speed gap and make it sort of less impactful and less noticeable, the gap between the CPU and memory speed and the disk speed. So you can see here the importance of the buffer pool and the techniques it uses to address this speed gap problem. Yeah. So to summarize, the buffer pool, when we load the pages from disk to memory, we try to keep them as much as we can, with the hope that some future queries will make use of them, and we save the trip to the disk. Okay, even if somebody changes, some other queries change those pages that are in memory, we don't go ahead and save them immediately. We keep the dirty ones on the buffer, and we wait until such time we need to throw out that particular page. Then we go ahead and push it to disk. And all of this is just to save time and to boost the performance. Now, at a certain stage, we will run out of memory, yeah, and we will have to throw out pages. Then there are multiple policies to do so. And one of the most widely used one, is the least recently used, but it has problems. It is very vulnerable to sequential flooding. If you have a query that reads so many pages, it might throw all your useful pages from the buffer. So but we have a solution for that. We go to those particular queries and say, okay, here is your cap. You cannot throw away all the pages. You will use this maximum number of buffers, and that's it. Don't throw away everything. And the other thing you can also do, the database does, for critical pages, such as the root page of an index, it is flagged with some high priority flag to let the buffer not to throw it away in any case. Okay. The other thing is the buffer pool tries to make kind of make use of the knowledge that we have about the layout of the table and try to prefetch pages that are likely to be used by the query. It knows. So the database has the smartness, because it has a lot of information at hand. It tries to make use of that to prefetch pages before they are requested. Okay, so this is to summarize. The I/O times dominate the BMS performance. This is the component that makes it or breaks it in terms of performance. In fact, the performance of a query, when we measure the performance of a query, as we will see in subsequent lectures, how do we measure the performance of query? Is it the amount of time it takes to process in memory? It's just the number of blocks it reads and writes. So if I want to quantify, for example, the cost of this query. Can you see here? What is the cost of this query? 1, 2, 3, 4. 4 IOs, 4 reads. Luckily, if buffer pool is well managed, the first one it will always be in memory. So what is the real cost? 3. Yeah, maximum. Hopefully, even some intermediate node, if the database the database server is a fat server with a lot of memory and not many competing processes, it can leave even some. Hopefully, some of the intermediate pages could also be left, and we can answer it all from memory. But in all cases, I can basically answer this query in 3 reads. In 3 reads, I am done. I read 3 blocks and I answer the query. So the cost, when I cost this particular query, I will say this query requires 3 reads. I ignore all the processing done in memory, or everything else I can safely ignore. Why?
It's much faster.
Because very, very fast. When compared to reading from disk is nothing. So that's why we ignore all other processing when we compute the cost of a query. We basically express that cost in terms of how many blocks we need to read or write. That's it. We can ignore all other aspects. Now, the database does not raise the white flag and say, okay, this is the reality in the ground. CPU is super fast because it's all electronic. It's a kind of light speed. I cannot compete with something mechanical, some arm moving. And no, it does not give up. It basically uses a lot of techniques to try to bridge that gap or reduce the impact of that speed gap. One of them is to use a buffer pool with some smart mechanisms to try to keep these pages we worked hard to bring from disk to memory, to keep them as long as we can. It makes use of a RAID technology. This is the disks, putting multiple disks in parallel. I'm basically writing to them in parallel, reading from them in parallel to speed up the read and the write. Very important, storing related data, contiguous blocks. So the data related and should be stored physically next to each other. So when we read these blocks, we don't need to do physical movement of the disk. physical movements of the arm. So, sorry? Yeah. So because remember, the disk, the enemy of the disk is to ask it to do random reads. Jump here, jump there, and get me the blocks. That will slow down your query performance. It's not like memory. Memory, you can do random access. It's same whether you're accessing basically a memory frame next to each other or randomly, no difference. But in a disk, it makes a major difference. So you try, as we will see through, for example, through indexing, try to keep the related blocks next to each other. So when you read them, you can read them together. Okay. And to do this, sometimes when you have a heavy database, this will become clear when we start looking at indexes again. You try to keep the blocks next to each other, but sometimes you have no other choice but to put certain blocks in another place. Yeah? So in this case, you have to do some kind of reorganization periodically in your database to make sure the blocks are contiguous. What I mean here, just to give you a small example, let's say we are storing, let's say, students by ID and sorted by ID. And for some reason, some new student comes and their ID, we need to insert it in between these two. Let's say we have two blocks and we want to insert this new student happens to be between these two blocks. But the problem with all blocks are full. Yeah? So now if we try to put it in one block, we have to move all the blocks. We cannot afford to do that. Yeah? So we can put that block in another place in disk, and then we link it to wherever it's supposed to be. So when we are, let's say if we are reading all the students, we have to, all the blocks will be contiguous, except this new one that we have inserted will be in another place. So that will degrade our performance. Yeah. So from time to time, the DBMS administrator, they run some scripts. Most databases, they have scripts to reorganize the blocks to keep them contiguous. So for example, this new student record that was stored in another block, which is not contiguous with the remaining blocks, we bring it in, put it contiguous, and push all the other blocks, push the other blocks to make some space and keep all the data sorted. Yeah. So what I mean here, lots of smartness goes into the DBMS to really address this speed gap, and those are the techniques that are used.